Our mission is to develop a lower leg rehabilitation device that's centered around the patient by being easy to operate, meaning it requires no assistance so they can be independent. It'd be lightweight and comfortable so that will encourage wear from the user, therefore increasing the patient compliance. This leads to a better and faster recovery, and the device will also help prevent re-injury during the healing process, which can often lead to more damage for the patient.
All of these factors we considered before creating our design led us to this design of the artificial muscle. This slide shows the different SOLIDWORKS parts we designed to be 3D printed in order to create the final model. The assembly model of all these parts is shown in Figure 1. The top right corner shows the internal skeleton that we 3D printed. This part was sealed after printing between 2 layers of thermoplastic. The idea behind this was to create an airtight seal that makes a pressurized environment which can cause the skeleton to expand or contract. Figure 3, which is right below the internal skeleton, shows the leg clamp we created that would be printed twice, with one aimed to fit around a person's calf and the other to fit around the person's thigh. The leg clamp was made to have a hollow rectangular extrusion on it that was meant to house one end of the internal skeleton. Each clamp would hold an end of the internal skeleton so that when it contracts, the clamp on the thigh will pull on the back of the person's thigh, generating an upward force. This figure shows that the clamps are left open to go around the leg, which meant that they needed to be connected around the back so this upward force could be generated. This is why we created the part shown in Figure 4. This connecting part was designed as a hollow shell that allowed the 2 ends of the clamp to slide into it, thereby connecting the clamp around the person's leg.
Here we can see the artificial muscle device lifting a spool of TPU. The spool weighs 2 pounds, or approximately 0.907 kilograms. The full contraction was 8.2 centimeters in a time of 6.65 seconds, which equates to an acceleration of 0.000185 meters per second squared, and a force of 1.68 times 10 to the negative 3 newtons. In this video, we see the artificial muscle device lifting a barbell. The barbell weighs 2.5 pounds, or 1.134 kilograms. The contraction is 7.4 centimeters in a time of 7.06 seconds, which equates to an acceleration of 0.00148 meters per second squared, or a force of 1.68 times 10 to the negative 3 newtons. Here we can see the artificial muscle aiding in the sit-to-stand motion.
Throughout our research, we've seen a variety of other knee rehabilitation devices, ranging from a simple slip to cover the knee to a full human body suit used by the military. While there are other sit-to-stand devices on the market, they tend to be bulky and unappealing to the patient, whether through too technically complex or not user-friendly. There are other devices being published that use rotating actuators to aid in the gait motion, however, none focus solely on the sit-to-stand while using this method. Our device is incredibly strong and able to support exponentially more than its own weight, and our design allows for the user to feel more comfortable not only wearing but also operating the device, which ultimately sets us apart from other competitors on the market.
The exoskeleton may be produced in different shapes by modifying the design such that it can help other body parts like the ankles, hands, neck, and arms. The long processing time of 3D printing the inside skeleton can be diminished by changing to a mold and curing approach. The noise from the air pump is a problem to be solved. A passive noise reduction system might be implemented, including a vibration reduction. In this way, our next work should discover a balance between noise reduction, volume control, and total weight.